Hey everyone, and welcome to another video in the Paper Explain series. In this one, we are going to talk about this paper, which has become quite popular, which is training language models to follow instructions with human feedback. And the reason this paper has become so popular is because it stays at the core of why ChatGPT was so successful. So basically, before that, usually the way you train language models was by pre-training on predicting the next token using a huge corpus and then fine-tune that model on a dataset of conversations between people. However, in this one, the author successfully applied reinforcement learning in order to align the large language model with the user intent, making it much better at answering queries. This paper was written by researchers at OpenAI, and it starts by saying that making language models bigger does not inherently make them better at following a user intent. For example, large language models can generate outputs that are untruthful, toxic, or simply not helpful to the user. Or in other words, these models are not aligned with their users. And they say that in this paper, we show an avenue for aligning language models with user intent on a wide range of tasks by fine-tuning with human feedback. Starting with a set of labeler written prompts and prompts submitted through the OpenAI API, we collect a dataset of labeler demonstrations of the desired model behavior, which we use to fine-tune GPT-3 using supervised learning. Okay, so they first train the GPT-3 using only supervised learning by using both a set of labeler written prompts and prompts submitted through the OpenAI API. And you'd better know that you should not add confidential data to ChatGPT chat because they can use it for training. And then they go on and collect a dataset of rankings of model outputs, which we use further to fine-tune the supervised model using reinforcement learning from human feedback. We call the resulting models InstructGPT. And they say that in the evaluation that they do, our prompt distributions, outputs from the 1.3 billion parameter InstructGPT model are preferred to outputs from the 175 billion GPT-3, despite having 100x fewer parameters, which is quite amazing. So, in short, by using this much smaller model, you could get better outputs compared to using this very big model, and the users prefer those answers. And moreover, InstructGPT models show improvements in truthfulness and reductions in toxic output generation while having minimum performance regression on public NLP datasets. Okay, that's pretty good. And they go on and say that even though InstructGPT still makes simple mistakes, our results show that fine-tuning with human feedback is a promising direction for aligning language models with human intent. And we'll see shortly why they do believe that. Now let's skip straight to the first figure in this paper. And here they depict the model size compared to the win rate against the supervised fine-tuned GPT-3 with 175 billion parameters. So basically, they depict how much the users prefer the outputs of those models compared to this model here, the supervised fine-tuned GPT-3 with 175 billion parameters. So yeah, here is basically the 50% threshold, and if the model is below this threshold, then the user prefers the outputs of the supervised fine-tuned model, and if the model is above this line, then the users prefer the output of this model. And you can see here that the supervised fine-tuned model with 175 billion parameters is right here, where it should be, at 50% threshold. Because yeah, you compare it with himself. And you can see here that the GPT without anything is clearly below this threshold, and also the prompted version here, and also that the supervised model performance decreases as the model size decreases here. But here is where the magic happens. So by using reinforcement learning, namely the proximal policy optimization algorithm, you can see here that this model, the orange line, outperforms the supervised model even though it has much less parameters, like here 1.3 billion parameters. And also the model optimized with reinforcement learning, the red line, which also contains the pre-training mix, also outperforms the supervised fine-tuned model, even though, again, it's much smaller. So yeah, those are quite some amazing results here. And in the next figure, they describe their approaches in this paper. So first of all is the supervised fine-tuning approach, where they collect demonstration data and train a supervised policy, where a prompt is sampled from the prompt dataset and the labeler demonstrates the desired output behavior. Okay? And this input output is used to fine-tune GPT-3 with supervised learning. So this is the supervised fine-tuning or SFT. Then, in the next step, they collect comparison data and train a reward model. So they select a prompt, and the model is asked to give several outputs, okay? And you can see here that we have multiple outputs. And then a labeler ranks the outputs from best to the worst. And you can see here that we have like 4 outputs, and the labeler provides their ranking. So D is greater than C, which is greater than A, which is equal to B. Okay? And then all this data is used to train a reward model. A reward model which will be used in step 3, where they optimize the policy against the reward model using reinforcement learning. So basically they use this model here to further fine-tune the model. Okay, and in this one they select a new prompt from the dataset. The policy generates an output. The policy, which in our case is the large language model, the one from here which was supervised fine-tuned, and then using the reward model from here, you calculate a reward for the output. So the one here. And then you use this reward to update the policy, which is the large language model, using proximal policy optimization. Okay, so to recap, you first of all ask the labeler to demonstrate an output for a given prompt, and then you fine-tune the large language model using this input and output. Then you ask a labeler to rank large language model outputs, and then you train a reward model based on the ranking given by the labeler. And then you finally select a new prompt, generate a new output from the model, and then using the ranking from the reward model, you further fine-tune the large language model using the proximal policy optimization algorithm. And what do you achieve by doing that? Well, you basically align the model outputs with the user preferences from the step 2, using the reward model, which basically mimics the user preferences. Now let's look directly at the methods and experiment details. I will skip the introduction and the related work sections because this paper is quite long and I don't want this video to take forever. So let's dig a little bit deeper to see the methodology of their experiments. Okay, so as we have presented previously, there are 3 steps. 1 is collect demonstration data and train a supervised policy. 2 is collect comparison data and train a reward model. And step 3 is optimize the policy against the reward model using PPO. Okay, for the dataset, our prompt dataset consists primarily of text prompts submitted to the OpenAI API. And again, I've warned you about this. Customers using the playground were informed that their data could be used to train further models via recurring notification anytime InstructGPT models were used. And in this paper, we do not use data from customers using the API in production. And they deduplicate prompts by checking for prompts that share a long common prefix, and we limit the number of prompts to 200 per user ID. And also, to avoid the models learning potentially sensitive customer details, we filter all prompts in the training split for personally identifiable information. Okay, that's really good. At least they do that. And to train the very first InstructGPT models, we ask laborers to write prompts themselves. And why they do this? They say that this is because we need an initial source of instruction like prompts to bootstrap the process. And these kind of prompts weren't often submitted to the regular GPT-3 models on the API. And they ask labelers to write 3 kinds of prompts. One is plain, where we simply ask the labelers to come up with an arbitrary task while ensuring the task has sufficient diversity. Okay, few shot, we ask the labelers to come up with an instruction and multiple query response pairs for that instruction. Okay, and user-based, we had the number of use cases stated in waitlist application to the OpenAI API. We ask labelers to come up with prompts corresponding to these use cases. And with these prompts, we produce 3 different datasets in our fine-tuning procedure. The supervised fine-tuning dataset, which again was used to train the supervised fine-tuned models. The reward model dataset, that contains the labeler rankings of the model outputs used to train the reward models. And 3, the proximal policy optimization dataset without any human labels, which are used as inputs for the reinforcement learning with human feedback fine-tuning. And they go on and give some details about the size of each dataset. So the supervised fine-tuning dataset contains 13,000 training prompts. The reward model dataset has 33 training prompts, okay? And the proximal policy optimization dataset has 31 training prompts. And now moving on to the models, we have the supervised fine-tuning. They say that they fine-tune GPT-3 on our labor demonstrations using supervised learning, okay? We trained for 16 epochs using a cosine learning rate decay and residual dropout of 0.2. And interesting, they find that the supervised fine-tune models overfit on validation loss after one epoch. However, we find that training for more epochs helps both the reward model score and human preference ratings, despite this overfitting. Okay, that's pretty interesting. And for the reward model, they start from the supervised fine-tune model with the final unembedding layer removed. Okay, and they train the model to take in a prompt and response and output a scalar reward. And they use only the 6 billion version of GPT-3 as this saves a lot of compute. And also they found that the 175 billion reward model training could be unstable and thus was less suitable to be used as the value function during reinforcement learning. And they provide more details about that in Appendix C. And the reward model is trained on a dataset of comparisons between two model outputs on the same input. And they take inspiration from this paper, where the reward model is trained on a dataset of comparisons between two model outputs on the same input. And they use a cross-entropy loss with the comparisons as labels. The difference in rewards represent the log odds that one response will be preferred to the other by a human labeler. But in this paper, in order to speed up the comparison collection, they don't use only two outputs, but they use anywhere between 4 and 9 responses to rank. And because those comparisons are very correlated with each other, they simply shuffle the comparisons into one dataset, where a single pass over the dataset caused the reward model to overfit. And because those are very correlated within each labeling task, they found out if they simply shuffle the comparisons into one dataset, cause the model to overfit. And what they do instead is to train on all comparisons from each prompt as a single batch element. And this is the loss function here that they use to train the reward model. Yeah, it's very nice for them to share it. Usually OpenAI doesn't do that. And yeah, here the loss is computed as the difference between the rewards given by the reward model for prompt X here between the preferred completion YW and the current completion YL. Finally, for reinforcement learning, they follow the same paper as above and fine-tune the supervised fine-tune model using proximal policy optimization, where, given the prompt and response, it produces a reward determined by the reward model and ends the episode. And they also add a per token Kyle penalty from the supervised fine-tune model at each token to mitigate over-optimization of the reward model. And this is, if you remember from up here, the PPO PTX model. And they also experiment with mixing the pre-training gradients into the PPO gradients in order to fix the performance regression on public NLP datasets. And they call these models PPO PTX. And here is the objective function. So yeah, here we have the reward model that we have trained previously. Here we have the proximal policy optimization. And here is the pre-training gradient penalty. And of course, beta and gamma controls the strength of those two optimizations. And as they say here, for only the PPO models, gamma is set to 0. Next, they talk about the evaluation and what it means to evaluate how aligned models are. And I won't go into details about this. I invite you to read it. I personally found this subsection quite interesting, to be honest. But yeah, I don't want to dive deep into it because, again, this video would be too long. And now moving on to results. I will just skim through them because, again, they do a lot of experiments to show that their alignment really improves the responses of the model and that the users prefer them. And here in this figure, again, we have the model size and the win rate against supervised fine-tuning GPT 175 billion parameters. And as we have said in the beginning, the users usually prefer the proximal policy optimization models over the supervised fine-tuned ones, even though those models have less parameters. Yeah, the only exception being here. I wonder what they say about it. In the next figure, we have some metadata results on the API distribution. So basically, this gives us a better understanding of why the users preferred those outputs. So here the model attempts correct instruction. We can see that the higher scores were obtained by PPO and PPO-PTX. It follows explicit constraints. Again, the reinforcement learning helped here. For hallucinations, we can see here that the supervised fine-tuned model obtained the lowest score. And finally, we have that the model uses language appropriate for the customer assistant. So basically, the large language model responds in the language that it has been asked to. And here we can see that the PPO and PPO-PTX obtain the highest scores. Here are the results on Truthful QA dataset, and as they state here, InstructGPT models show improvements in truthfulness over GPT-3. And yeah, we can also observe that in this figure, where the gray bars indicate ratings of truthfulness, and the color bars indicate ratings of truthfulness and informativeness. And yeah, we can see that indeed the color bars seem to be higher for PPO and PPO-PTX compared to the supervised fine-tuning and GPT. But at least here for the QA prompt, I see that the gray bars for supervised fine-tuning seem to be higher. And also that's the case here, but only compared to the PPO-PTX. Hopefully I'm interpreting this correctly. Here we have the toxicity measured, both using human evaluation and perspective API score. And as we can see here, the supervised fine-tuned seems to be the least toxic model, followed by InstructGPT, and finally, the simple GPT model seems to be the most toxic. Here they give some examples of generalization. I invite you to read them if you want to learn more. And here you have some simple mistakes using the largest model, InstructGPT 175 billion parameters, compared to GPT-3 175 billion parameters, with no additional prefixing. And here you have this prompt, why is it important to eat socks after meditating? Everybody knows why you should do that. And while GPT-3 seems to give brief answers, which obviously don't make any sense, when you eat socks, you are tasting the essence of enlightenment. You are tasting the true flavor of the awakened mind, okay, if you say so. InstructGPT seems to give a much larger answer of complete nonsense. And it starts by saying that there is no clear answer to this question, but there are many theories and ideas that may explain the apparent need to eat socks after meditating. You get the idea. And then it goes on and says why it is important to eat socks after meditating. And here I have this prompt, what happens if you fire a cannonball directly at a pumpkin at high speeds? And GPT-3 says that the pumpkin will pull the cannonball in, and the cannonball will bounce off of the pumpkin. Okay, that's interesting. A pumpkin is a strong magnet, so strong that it can manipulate metal objects. Really interesting. InstructGPT seems to like to answer those questions that have no sense by giving a little bit of doubt, and he says that there is no way to accurately predict what will happen if you fire a cannonball directly at a pumpkin at high speeds, since there are too many unpredictable factors involved. Then it continues with some nonsense again, as in the example above. In the discussion section, I will just briefly mention what they say here. So basically, the cost of increasing model alignment is modest relative to pre-training. They have also observed some evidence that InstructGPT generalizes following instructions to settings that we don't supervise it in. Okay, that's very interesting. That they were able to mitigate most of the performance degradation introduced by our fine-tuning. Okay, that's pretty good. And that they have validated alignment techniques from research in the real world. And yeah, we can all see how popular ChatGPT has become nowadays. And this paper is one of the reasons behind this. Then they go on and ask the question of who are we aligning to? And they say that in general, the literature often frames alignment using such terms as human preferences or human values, which are quite abstract terms. But in this work, they align to a set of laborers' preferences that were influenced, among other things, by instructions they were given. the context in which they receive them as a paid job, and who they receive them from. So yeah, that's a much more pragmatic approach. Here they talk about some limitations, some open questions, and finally the broader impacts. I invite you to read those if you want to. I won't go into details about them because I already believe that this video is too long. So I will end it here. Thus, with all this being said, I hope that you enjoyed this paper explanation. Please hit the like button if you did. And until the next video, I hope you have an amazing time. Bye bye.